Hi, everybody. It is week 13, and this week we are going to talk about water, some of its properties, and we're going to get into solutions. So here's our story so far. We've talked a lot about chemical reactions, types of reactions, and energy taken in, energy given off. But many of the reactions that we have worked on have occurred in aqueous solutions. In order for ions to switcheroo and for partners to change in chemical reactions, that has to be in water. A lot of the chemistry that occurs in the human body must be in water. Well, in a watery solution usually refers to being in an aqueous solution. So that's why we're going to spend this week talking about what is a solution, types of solution, parts of solutions, how do things dissolve, and electrolytes. But we're going to start out with our first topic, properties of water. Now we all know what water is. Water is H2O, fancy chemical name, dihydrogen oxide. It is a colorless, odorless, tasteless substance that in our daily lives we see in all three states of matter: solid, liquid, and gas. And it's one of the few things we see on a daily basis in all three states of matter. It covers about 70% of the Earth's surface, and it makes up about 60% of the human body. If someone is ill or goes into the hospital or receives emergency care, one of the first things they are given is an IV solution because staying hydrated is so incredibly important. Now, the structure of water has a lot to do with the properties of water. So let's go into the chemistry of it. This H2O molecule is covalently bonded. If you remember, covalent bonds means that they share electrons, and they share electrons like this. Oxygen is a group 16 element. That means it has 6 outer electrons. Hydrogen is a group 1 element with 1 outer electron. And so oxygen, with its 6 outer electrons, is going to go around like this. Hydrogen has 1 outer electron. And when the water molecule is put together, it comes up with a structure that looks sort of like this. This is the Lewis dot structure for a water molecule. Now, that Lewis dot structure of the water molecule gives us a vague idea, but when we really examine the water molecule, it looks more like this. The molecule has a bend in it. This is not a 90-degree bend. Actually, that bond angle is known very precisely. It's over 90 degrees. It's 104.5 degrees. And you go, why do I care? Well, you don't 100%, except we know this angle very precisely because we have studied water so incredibly much. Oxygen is a much larger attractor of electrons than hydrogen. So what that means is the front end of the water molecule is going to have these unpaired electrons. And so the front end of that water molecule is going to be more negative, and then the back end of that water molecule is going to be more positive. That makes water a polar molecule. Now, it's neutral, meaning it has the same number of positive and negative charges. It's not an ion. It is a molecule, an uncharged molecule, but it's polar, just like the Earth has a north and south pole, just like a magnet will have a north and south pole. One end is slightly different from the other. And this really helps explain a lot of the characteristics we see. We use the term electronegativity to describe that polar properties of any sort of chemical. So the oxygen end of the water molecule is a little more negative electron in the electronegativity department, and the hydrogen end is a little more positive in terms of electronegativity. This symbol, which is the lowercase version of Greek letter delta, is used often to describe the electronegativity. So you are going to see symbolism like this when you look at different molecules in different literature. One of the big rules of electricity is opposite charges attract. positives are attracted to negatives. So if you have a bunch of water molecules hanging around together, because it's hard to get one alone, what's going to happen is, because of that polarity of charge, because they are polar, what's going to happen is the oxygen end, which tends to be a little more negative, will line up with the positive end of the hydrogens, and they are attracted. Negative, positive, negative, positive, negative, positive. And those weak interactions, those electrical attractions that create these weak interactions between polar substances, those are hydrogen bonds. And back when we were talking about variety of different kinds of bonding, we talked about hydrogen bonds. Well, these little critters hold water molecules to other water molecules. And if you remember, these hydrogen bonds that occur not just with water, but anytime you have polar covalent substances, are responsible for all sorts of things, including water droplets holding onto windows, create the curl in your hair, which comes out when you wash your hair, the double helix structure of DNA, things that are weakly attractive, like your contact lens that goes in your eye, and yet you can easily remove it, Post-it notes, easy to remove tape, and then these hydrogen bonds that are created when you wash your jeans and easily broken when you spend the day in them, kind of wiggling your jeans out, and then they get washed, boom, and those cross linkages get recreated. Now, most substances, when they get colder, they get more dense, and this has to do with kinetic energy and vibration. Now, the bonds that hold elements together or compounds together, if you can kind of imagine them as a little spring, they're not solid things. They have some give to them. And when something is cold, the molecules kind of bounce back and forth due to their kinetic energy and their vibrational energy. When they get hotter and they have more kinetic energy, that bond is stretched out and they're going to bounce further from their rest position. So in a hotter situation, they have a tendency to be lower in density because the molecules have just more kinetic energy, more speed, and they're going to vibrate further from the rest position. If you could make something hotter still, it would vibrate even further from its rest position and be even less dense. That's most typical substances. But water is wacky, and water is wacky because when water freezes, its density actually goes down. It gets more fluffy, if you want to use that term, than when it is in a liquid. And this is opposite most substances. So let's take a look at this. When water is in a liquid state, it obeys up until 4 degrees Celsius. It obeys the typical normal rule that we expect, that when it is hot, it is less dense, and as it gets colder, it gets more dense. So this is pretty typical. Okay, this is very, very typical, and that is what we expect. But as it gets to 4 degrees Celsius, a weird and wacky thing happens. Because of this polarity of the bonds, because the molecules are going to orient themselves negative, positive, positive, negative, as it starts to go from a liquid state where the molecules are kind of all snuggled up together, it forms into a crystalline ring structure with a lot of open spaces in between, and it actually increases in size. It takes up more space. Well, if something takes up more space, it's going to end up having less or lower density. And what that means is you end up with the highest density of water is going to occur at 4 degrees Celsius. That means that ice floats on water. This is very unusual. Most solids are going to be much more dense than their liquid counterpart, but this gives us situations where ice is going to float on the top of your cold drink. Penguins can float on top of a little ice floe. Icebergs are going to be on top of the water and hence dangerous to shipping lanes. This is a very unusual situation. The other thing that occurs is this allows fish to survive the winter. So let's talk about how fish actually survive the winter. And we're going to look at the changes in a small lake or a pond through the seasons in a cold place like Wisconsin. So in the summertime, the sun shines down on a small pond or lake, and the water in this little pond is going to heat from the top down. So the top layer is going to be warm, and as you go down, it is going to get colder. And if you have ever gone swimming in a lake like this, you probably notice that your top half is kind of warm and your lower half gets a little cold, especially early in the summer. Now, as fall approaches, cold wind blows over the top of that pond. Well, what happens with the cold wind is the top layer of water gets cold. Well, cold water is more dense and it falls. So the cold water gets more dense and it falls. And as that cold water gets more dense and it falls, it brings the colder water up from the bottom and it goes to the top. So in the fall, there is a mixing of water that occurs, and the entire small pond or lake is going to turn over. You're going to have this big turnover. And let me just also say, this is assuming there is not a big underground spring feeding this, okay? Because that will change the fluid dynamics. As winter approaches, more cold wind is going to be blowing over the top of the pond. And what occurs is this gets colder and colder and colder still, but it gets colder until the entire pond is 4 degrees Celsius. When the entire pond is 4 degrees Celsius, a wacky thing happens. Because this is the temp at which the water is the most dense, it stops mixing. And because of the fact that it stops mixing, as it gets more cold wind blowing across the top and taking heat out of the water, the top layer cools down to 3 degrees Celsius, 2 degrees Celsius, 1 degree Celsius, 0 degrees Celsius, and it starts to freeze. And when it starts to actually freeze, because of the fact that ice is less dense than water, it starts to ice up and you have ice on the top of your pond. Well, as winter progresses, this ice gets thicker and thicker and thicker. But the fish down in the bottom are existing in nice, chilly, but still liquid water. Now, if water did not have this wild and crazy property of staying very dense and liquid at 4 degrees Celsius, what would happen is that the water would act like iron and gold and other solids. The pond would freeze from the bottom up. And if the pond would freeze from the bottom up, your little fishy would occupy less and less and less space. And ice fishing would be not very difficult, because what would happen as the ice froze is your fish would be in about a 6-inch layer of water at the top of the pond. You just go out and pick them up. But every single winter, the fish would totally freeze out. So the fact that fish can live through the winter is totally due to the polar nature of water. Cool, cool stuff. I love science. All right, have a grand day, and we'll talk to you later. Bye-bye.